Welcome to the Explainer. You know that feeling when you're staring at a coding problem and have no idea where to even begin? Well, a lot of the time, the answer's right here, with sorting and searching. Today, we're going to totally demystify these core algorithms. We're not just talking about how they work, but how you can use them to absolutely crush your next exam or technical interview. So here's our game plan. We'll start with why we even bother putting things in order. Then, we'll look at the slow way versus the smart way to sort. We'll even find out if there's a speed limit for sorting and what tools the pros use. And then, the grand finale. We'll unlock the real superpower that sorted data gives you and wrap it all up in a neat little toolkit for exam day. Ready? Let's jump in.
All right, first things first, why do we care so much about sorting? I mean, it seems kind of basic, right? But here's the thing. Sorting is like a secret weapon. It's a foundational step that makes a whole bunch of really hard problems suddenly incredibly simple.
Okay, let's kick things off with a classic interview question to get our heads in the game. You've got a jumbled list of numbers. How do you figure out if any number shows up more than once? Well, you could grab the first number, compare it to every other one. Then grab the second number, compare it to all the others. Ugh, that's a ton of work, and it gets ridiculously slow if the list is huge. There has to be a better way, right?
And there is. The moment you sort the list, the entire problem changes. Look, any duplicates are now forced to sit right next to each other. So instead of all those crazy comparisons, all you have to do now is walk through the list one time and check if any number is the same as its neighbor. It's that simple. Creating order brings clarity.
Okay, so sorting is super useful, we get it. But how do we actually do it? Let's check out the different ways to get this done, starting with the one that's easy to understand but painfully slow.
All right, let's meet bubble sort. Now, you learn this one in school, not because it's good, but because it's simple. The idea is you just keep passing through the list, comparing elements side by side. If a pair is in the wrong order, you swap them, that's it. The biggest numbers slowly, bubble their way to the top.
So check it out. After the very first pass, the absolute largest number is guaranteed to be in its final spot at the very end. After the second pass, the second largest is locked in. It works, for sure. After enough passes, everything will be sorted. But you can probably see the problem. It takes a ton of little swaps to get there.
So why is it so slow? What's the real bottleneck here? Well, to get a bit more technical, and this is a key term for exams, we can measure how messy an array is using something called an inversion. It sounds fancy, but an inversion is just any pair of elements that are out of order with each other. Every single inversion is a piece of the mess that the sorting algorithm has to clean up.
A perfectly sorted list has 0 inversions. A list that's perfectly backwards has the most inversions possible. And here's the crucial link. Since bubble sort only swaps neighbors, each swap can only fix one single inversion at a time. So in the worst-case scenario, you've got a whole sea of O(n)² inversions, and you're stuck fixing them one by one by one. That's where that O(n)² time complexity comes from.
But don't worry, there's a much smarter way to do this. Enter merge sort. This thing is an absolute powerhouse. And it's a beautiful example of a strategy you'll see everywhere in computer science. Divide and conquer. Instead of tiny little steps, it takes big, clever leaps. And the strategy is just genius in its simplicity. First, you just divide the list in half, and then you divide those halves in half. You keep doing this over and over until you're left with a bunch of tiny lists with only one item each. And guess what? A list with one item is already sorted. The real magic happens in the combine step, where you cleverly merge all those little sorted lists back together.
Now, the difference in speed here is just mind-blowing. O(n)² versus O(n) log n isn't just a little bit faster, it's a whole different universe. For a list with 1,000,000 items, bubble sort would take something like 1,000,000,000,000 operations. Merge sort, around 20 million. We're talking about the difference between grabbing a coffee versus waiting for weeks. It's a huge deal.
This all leads to a really interesting question, right? We went from O(n)² down to O(n) log n. That's a huge leap. But can we go even faster? Is there like a universal speed limit for sorting?
Well, for any algorithm that works by comparing elements, asking, is this bigger than that? The answer is a hard no. It's been mathematically proven that O(n) log n is the absolute best you can do. Think of it like a game of 20 questions. There are just way too many possible ways the list could be sorted, and each comparison only gives you a little bit of information. You simply can't figure it out any faster.
However, what if we could cheat? What if we could sort without comparing things? That's exactly what counting sort does. Now, there's a huge catch. It only works if you have integers that fall within a pretty small range. If they do, you can just create a separate array to count how many times each number appears and then rebuild the sorted list from those counts. It's shockingly fast, linear time, O of n. But remember that catch. A classic exam mistake is trying to use counting sort on data it can't handle.
Okay, let's get real for a second. You have a programming contest tomorrow. Are you really going to sit down and code merge sort from scratch? Let's talk about what you should actually do.
The answer is absolutely not. Please don't. In any practical situation, an exam, a contest, a job, you should always use the tools that are built into your programming language. These library functions are ridiculously optimized, they've been tested a million times, and they save you a ton of time and prevent you from making silly mistakes.
I mean, look at this. In most modern languages, sorting is literally one line of code. These things are so powerful they can sort almost anything you can imagine. So here's your homework. Find the built-in sort function for your favorite language and learn how to use it. It will be your best friend, I promise.
All right, now we get to the really good part. This is the biggest payoff, the main reason we go through all the trouble of sorting in the first place. It's not just about making things look neat. Sorting unlocks a genuine algorithmic superpower.
If your list is a mess and you need to find something, you have no choice but to do a linear search. You start at the beginning and check every single item. That's O of n. But once your data is sorted, you can unleash the lightning-fast binary search. And this runs in O of log n time, which is just ridiculously fast.
The logic is so simple and beautiful. It's just like looking up a word in a dictionary. You don't start at page 1, right? You jump to the middle. You see if your word comes before or after that page, and then you've just eliminated half the dictionary in one move. That's binary search. You keep checking the middle and chopping your problem in half over and over. To find one item out of a million, it takes 20 guesses, max. Insane.
Okay, that was a lot, I know. We went from the why to the how and beyond. So let's boil it all down into a simple toolkit that you can take with you straight into your next exam or interview.
Okay, screenshot this if you need to. This is your cheat sheet. You have to know these time complexities by heart. Think of bubble sort as a teaching tool, merge sort as your powerful everyday workhorse, and counting sort as your super fast specialized tool. And the most important takeaway of all, the incredible O log n speed of binary search is only possible because we pay the O n log n price to sort the data first. It's almost always a trade-off worth making.
And to wrap things up, I want to leave you with one final question to chew on. We know sorting is powerful, but is it always the right tool? Sometimes it's actually overkill. Thinking about problems like this, about whether you need the full sorted list or just a piece of information, is what takes you to the next level as a problem solver. That's a little hint about something called selection algorithms, but we'll save that for another time. Thanks for watching.